Then we're going to continue part 2. You definitely need to know the difference, okay? The difference between the concrete and cement. So the best way to understand is cement is just a part of concrete, okay? Concrete is nothing but we mix, right, some of the materials together, and one of them is cement. So the major ingredient of concrete is cement. So in formal words, cement coats the aggregates and bind the constituents together. It's just kind of like a glue that we use, glue the stones mostly. Concrete is, in formal word, we call that is a monolithic ceramic product, okay, of aggregates bonded with cement. Okay? So therefore, cement is again an ingredient in concrete and other materials. So here you can see the cement bag. This one is a concrete, and cement is a part of it, okay, because we also put other stuff into cement to make concrete. So here you can see a very beautiful building, and it's constructed with concrete curtain walls. Composition. So what's in the concrete? We have fine and coarse aggregates, okay? And your matrix is definitely cement. Here we're going to define cement as a monolithic ceramic aggregates. And these aggregates are bonded with cement. And we usually use Portland or asphalt cement. Concrete is a hydraulic material because water in it, we can make concrete without water. And it definitely hardens in water like cement because cement is in concrete and it hardens with water, Okay, just showing you a picture. And you can see the ingredients. And you can see the percentage, so they're used in different proportions to create the concrete. Okay, this is just a mixer. So we put 11% Portland cement, and then we're going to put 16% water, and we've got air too, 6%. This is very important. And we're going to add 26% sand. We call them fine aggregates. And we're going to add the 41% gravel. We call that coarse aggregate. This is just a table, and this table is showing you various concrete mixes used in different applications. So here we're going to make like an 8 inches basement wall. And you're going to need like 5 bags per yard of cement content. Your maximum size aggregate can go from here to here. And that's a 1 to 1.5 inches. We're going to put 7 gallons of water per bag of cement. So that's your water to cement ratio. And you have 28 a day compressive strength, okay, about 28,000. So if you want more strength, you want to put these parts according to this chart, okay. So the construction paper, they always have a chart like that. So it depends on the building and also the budget, okay. You will be following the mixture or percentage, okay, amount to make all these applications. We have 2 different mixture. One is rich and the other one is lean. So in rich mixture, we put 1 part cement and 1 part sand and 3 parts stones. In lean mixture, we put 1 part cement and we add like 3 parts sand and we're going to add 6 parts stone. Okay. And if you ever got into the construction industry and you are an industrial technologist, and sometimes you might have to calculate, okay, how many parts you might need to put into mixing, okay, machine like that. But then right now, And the labor market is definitely going with their own construction laborers, and they don't really hire the industrial engineering, technologists or industrial engineering personnel to do these works. So it's kind of like construction is kind of like going off market, off of our field today. But sometimes you might get those kind of positions, in construction companies, and your job, it's kind of like very vague in their environment, and you have to do everything that they want you to do. And one of the jobs is to calculate the mixtures, like that. It depends on the buildings that they're building. So classification, we have ready mix, and we have pre-cast, we have masonry, and the cement based. So here you can see that's a cement base, and that's your masonry ready-made things. This is your ready mix, and then that's your pre-cast. Ready mix, it is definitely made off-site. Off-site meaning it's away from the job site. So this is job site, and then they're going to transport the mix to the job site with a concrete truck. You can see concrete trucks all the time on the road. So about 75% all concrete made that way. So we use for footings, piles, walls, highways, and bridges. Precast, the same thing. Precast are the structural concrete components, and they are cast at a location away from the job site. And again, precast is delivered by truck. So your bricks and your bridge, girders, your wall panels, and your covers. Masonry, again, cast off-site. Then you have structural and the architectural products. So we have blocks, we have patio paving stones, and we have the residential, commercial, architectural units. You can find these at Home Depot, Lowe's. You have to order large loads directly from the parts manufacturers. Cement-based materials, they're again definitely manufactured off-site. So we have a mortar mix, the construction grout, terrazzo, roofing tiles, and then the concrete countertops. I love to make these. It's pretty. It's kind of fun. You can play with it. Tests. So we have 3 tests. So one is ASTM C143, commonly known as your slump test. ASTM C39, commonly known as your compressive strength test. ASTM C38 is your flexure test. The formal word is flexure strength of concrete test. We just call it slump test, compressive test, and flexural test. Alright, so slump test. We're just measuring how much concrete falls when removed from a frame. So in other words, it's just looking at how viscous the wet concrete is. It's going to stay, so you slump it up and see when it falls. So slump test is used to measure the consistency of the concrete. So if they are consistent, they won't fall fast. So the amount of slump depends on the amount of water or the type and size of the aggregates. So you can see here outside, that's a slump, So the test is performed by placing newly mixed concrete in a slump cone, and then the slump cone is placed on a flat surface, usually a plank or a slab of concrete, like that. And then slump cone is then filled with 1/3 full of concrete mix, and putting it 25 times with 5 by 8 inches bullets pointed 24 feet long metal rod. Putting it just stroking up and down, and then done to fill all voids in the slump cone. The next step, you're going to fill the cone with 2 by 3 full and puddle it again, 25 times. So finally that cone is filled completely in puddle of final 25 strokes. The excess is going to remove them from the top of the cone by using a straight metal like that rod and carefully walking back and forth across the top of the metal cone to level the concrete. And that process is referred to as a striking of the concrete, okay, just removing the excess. So once the cone is filled and excess struck off, the slump cone is carefully lifted from the wet concrete and set beside it. And then you're going to measure the slump by laying a straight edge across the top of the cone and over the concrete. And then you're going to measure the distance from the top of the cone and the top of the concrete is your slump. So the slump should remain consistent for a single job with each new mix of concrete. Okay. Otherwise, the concrete you are adding to the building wouldn't be consistent. So if you want a consistent strength for your building, you definitely need to do this slump test every time you mix. Yeah. So STMC 39 compressive strength test. I'm thinking to add calculation because in this, I think the assignment question sets from the textbook. Okay, they're gonna ask you how to calculate, and this is one of them. So make sure you know how to do it, so you wouldn't have any kind of issue during your final exam. So here it's just showing you the testing procedure. Okay, involves applying a universal load because we're getting into compressive strength, so we're going to use a test instrument like this. So you'll put a universal load on each specimen until it fills. Universal means we're using a standard load. And then you're going to calculate the compressive strength and the cross-sectional area of that cylinder and apply load as needed. So we use the compressive strength formula. Your sigma is equal to load divided by CSA is your cross-sectional area. So here is an example how to calculate it, and the load is given as 98,000 pounds. So we're going to put it, okay, into the equation, so 98,000 pounds. And the specimen diameter is 6 inches, so that's the diameter, but we need the area, yeah? So the cross-sectional area is pi r squared. So you're going to calculate it. Pi is going to come the value from your calculator times. This is the diameter, so divide that, okay, by 2 and then square it, multiply with pi, and you're going to get 28.27 inches squared. Put that in, okay, as the CSA. Calculate this ratio, and you're going to get 3466.57 psi. So I think the only, here in this example, the cross-sectional area is given to you. In the test, I'm going to give you just the diameter, and you should know how to calculate that. Okay, so if you have a diameter, so when you go to the little circle like that, you're going to see that's the diameter. Okay, so circle has a center. So if you want to get the R, which is your radius, okay, this is your little R, you will have to divide this diameter D, okay, from here all the way to here by 2, okay, because the center is cutting it into 2 equal parts anyway. So you will get your R, and then you're going to put it into the cross-sectional area. Formula is your pi, right, and then times r squared. It's really difficult to write. So you're going to put that value in r, square it, times pi. Pi is going to come from your calculator, okay? And you'll definitely get the CSA, which is your cross-sectional area. Okay, let me erase this mess. So make sure you know how to calculate this. Okay. So compressive strength this test is very important because it is an important property of concrete. So we always do this test, okay? This is like an old testing instrument. Anyway, it looks like that. So you put a little block of concrete right in there and then test it. So here's a test age 24 hours, 3, 7, 20, and 90 days. So this table is showing the time tolerance for concrete compressive strength tests, okay, and we're following the ASTM. So here the permissible tolerance is your standard deviation, which is plus or minus 0.5 hours or 2.1%, so and so. Yeah, depends on your test age. But again, I don't worry about how to use them. You don't need to know this. This is just engineering part. Your part probably is going to be just unless you go into construction industry, okay, you wouldn't have to do these things. So just try to know that's how we do for the compressive strength for concrete. Okay, STMC 39 compressive strength tests. So they're just the growth, and they show the water content and the compressive strength of concrete over time. Again, water content is so important in concrete because this material hardens the concrete, and we need the concrete to be hardened, okay? Because the strength comes when it becomes so hardened, yeah? So here is a 1 day type 1 Portland cement, 3 days type 1, 7 days type 1, and then 28 days type 1, and we're testing Portland cement. And here is your compressive strength, and we're using the PSI for the unit. And this x-axis is going to give you the gallons of water per sack of cement, meaning how many gallons you're putting for 1 bag of cement. And you can see how the graph goes up, yeah, compression strength goes up as you have more and more days, so 1, 3, 7, and 28 days, yeah. The same type, by the way. ASTMC 78 is your flexion strength test. It's a little bit different, the instrument is. So here we're using a little bit longer load. So when the concrete is placed in bridges, floors, and roofs, and tensile strength is very necessary to be tested because we need the concrete to be very strong to support many different vehicles with different weights, you know, passing over it. So the floor is the same thing, okay, because floors are built one floor over another in the skyscrapers, and also roofs, the same thing, you know, very important. Of course, the concrete roofs we're talking about. So a true measure tensile strength of concrete is very difficult. So even though we're testing, we're not getting the true measurement of your tensile strength, okay? Because it's really difficult to grip the specimen to apply a true tensile force. Okay? So we can't get the force right. Therefore, you can get the tensile strength true value, but we can get approximate, okay? And that's good enough. So the bending test, that's your bending test, provides a measure, and we're looking at the modulus of rupture, MOR. We have already seen this before. So the MOR is closely related to, again, the tensile strength. So ASTMC 78 flexural strength test is just a standard test to determine the flexural strength of concrete. The test specimen, you have to choose it, and it got to have a span 3 times its depth, okay? And that's within 2%, meaning the span got to be within 2% of its depth. And the size of the specimen must be at right angles to the top and bottom surfaces. So you have a two surface, the top surface, and then the bottom surface. And the size of that specimen got to be right angles to that two surfaces, okay? So all surfaces that are in contact with the load and support blocks, they got to be smooth, they got to be free of scars, indentation, holes, or inscribed identifications. So here, that's how we're putting, okay? So the load on the specimen may be applied rapidly, up to 50% of the assumed breaking load. Breaking load meaning like if you put that amount of force, your concrete is going to break. So the load must then be reduced to 125 to 175 psi. So this load rate is held until failure happens. So the maximum loads we usually measure in pounds in the US and kilograms outside, and is recorded and used to calculate your modulus of rupture. So here you can see how to conduct a flexion test of concrete, and it will be a little bit difficult for you to be able to see it. So here you can see the load in the specimen is right here, yeah, and this is your top and then the bottom surface. It's easier to see in this cartoon. So your force of the load is right there, and your test bar of concrete is right here, and then this is your surface, okay, and this is also your surface, and then your force is on this side as well. So the flexion test and the compression test, they kind of look very much alike, but then how you apply the force is a little bit different, yeah? So here you should know your span length is going to be from here to here. That is one, okay, within the 2% of your depth. So here, that's the battle testing machine right there. And this is your depth, is going to be L divided by 3. And your L is 1, 2, 3, 3 times of your 1/3, okay? So STM C78 fractional strength test use this MOR, which is your modulus of rupture equation. So here in this equation, you can be able to calculate modulus of rupture from maximum load, which is your P, times the span length, which is your L, divided by the width of the specimen, and then the average depth of the specimen, okay? So don't forget you have your length, the width, and then the depth. So the B and D you determine by taking measurements at each edge and also at the center. Yeah. Fiber reinforced concrete has been we've been reinforcing the concrete one way or the other because we want to overcome the brittle nature of that and also improve its tensile strength. So traditionally we use our reinforcing materials like steel wires or solid round steel bar stock. Solid bar stock you can get them from Home Depot or Lowe's outside, okay, for the non-commercial purposes or small buildings. We call them rebars. It's short for reinforcing bar. So even though the steel is very popular, we're now using the fibers, okay, to reinforce concrete. So fibers are made from a variety of materials. We use glass. These are all recycled, by the way. Most of them are. And Kevlar, and then polypropylene, nylon, and cellulose. So we add the fibers to strengthen the concrete, also to improve its ductility. So when a crack happens in a brittle material, these cracks, they tend to grow. We want to stop that. Okay, in order to stop that, we add the fibers. That growth of crack, okay, from a smaller crack, we call that the crack propagation. So reinforced concrete, we're trying to stop that crack propagation by adding other stuff, yeah, into it. The fibers used to reinforce concrete, they're kind of short and they're not continuous, meaning like they're in pieces, yeah, and they're placed randomly in the concrete mix. Just mix them up. In Japan, we use the fibers a lot, right? Especially in making the airport, and also we use a lot of the recycled material in the concrete to strengthen the concrete. It's one of the Japanese methods that we're getting. So these fibers tend to stop a crack from propagation. So the fiber reinforced concrete types are low fiber volume composite and higher fiber volume composite. And we have a high fiber volume composite. So when you take a look at the low fiber volume composite, so it has like about 1% fiber, okay, not much in it, and it's used for the field application, containing large volumes of concrete. So if you think about the low fiber, you have low fiber with a lot more concrete in it. And we use them for paving roads, because roads, we don't want the cracks. Even when you go outside, pay attention to the roads, and you're going to see cracks, right? And in order for us to stop that or control the cracking, you're going to use a low fiber volume composite concrete. They definitely do not increase significantly in the strength of the concrete, okay, but definitely stop the cracks. So higher fiber volume composite typically used with a tin, right, thin sheets like that, and then you're going to mix it with the cement mortar mix, which is your concrete. So the fiber volume in this mix ranges from 5 to 15% of fiber in the concrete. High fiber is the highest, so it has the greatest volume of fiber reinforcement, and it definitely increases the strength and also toughness. So the reinforcements are usually a sheet material like this, and the concrete is used in roof and wall panels, right? We don't want these to fall out, so therefore we definitely need to increase the strength so that the concrete, okay, is going to stay up with this reinforced material. So the fiber volume here, we have about 40%, so that's pretty high. So that is for Unit 7, Part 2. Cement and concrete is a small chapter and it's easy to follow. So I think you have no problem doing the assignments, and just pay attention to that calculation, okay?